For the benefit of those who are just going to be watching the video on YouTube, we're not going to have a midterm next week, and I'll send out an email talking about that. Okay. Let's try to wake up a little bit. What were we doing last time? We were talking about transitive relations. Transitive relations. Can someone remind me what a transitive relation is? By the way, are things visible, or do I need to like close applications so that my computer can properly show you? Looks good. Okay, cool. So what's a transitive relation? What's the condition? Yes, exactly. A relation is transitive. A relation R on A, which remember this means R is a subset of A cross A. Relation R on A is transitive if how do I want to say this? If A comma B and B comma C in R imply that A comma C is in R. So we went through kind of some examples of relations that were kind of mathy, namely, I don't know, we had a big list of examples. I'll produce another big list of examples today before we continue. But let's kind of go back to our game where we were trying to find relations on the set of people, which are, so let's find relations on the set people, which let's say are transitive and are not transitive. Can't even write anymore. Just falling apart at the seams. What's a transitive relation on the set of people? A has the same birthday as B. That's a good one. So A and B is in R if A has the same birthday as B. Right? Because if A and B have the same birthday and B and C have the same birthday, then A and C have the same birthday. A is taller than B is also a good one. So A, B, such that A is taller than B. Because if A is taller than B and B is taller than C, then A is taller than C. Siblings. Yeah, siblings is another thing that's transitive. So A, B is trans, so yeah. A and B are siblings. Another one is like descendant, right? Here's one, A and B if A is a descendant of B. Great, tons of examples. How about some relations on the set of people which are not transitive? A has more pets than B is going to be transitive, right? Yeah, friends. Friends are not transitive. A comma B such that A and B are friends. This is definitely not transitive. Or similarly, something like A and B such that A has shaken B's hand. Definitely not transitive. What's another relation that's not transitive on the set of people? I think that is correct. That is not transitive, right? So A, B, such that A is the child of B. And this is a good example because you'll notice there's a relationship between this one and the descendant relation. So the descendant relation is transitive because if A is a descendant of B and B is a descendant of C, then A is indeed a descendant of C. But when you look at the child relation, then that's kind of like a one-step thing where descendant covers any number of steps, but if A is a child of B and B is a child of C, that does not mean, and hopefully does not mean, that A is a child of C, unless you're in like 100 Years of Solitude or something, reading Marquez. But these two are kind of related, and they're related in a way that we'll see pretty soon. Related. Well, that's the wrong word to put there. But any questions on some of these examples, or are we feeling kind of comfortable with transitive relations? Doing all right? Cool. Okay, so those are three very important properties about relations. I'm going to introduce a couple more things that we can do with relations. So first, let me get a bunch of examples just so that we can play around with these things. Let's have R1 be, I'll do kind of similar ones to last time. It's a subset of the reals cross the reals such that A is greater than or equal to B. That's a relation. R2 is going to be the set of all A and B such that A is less than B. That's cool. R3 is going to be the set of all A and B such that A is equal to B or A is equal to negative B. These are kind of familiar. R4 is equal to the relation A and B such that A plus B is less than 3, say. These are some relations that we can play around with. Okay, my point is that relations are a subset of A cross A. So let's say I have two subsets of A cross A, or say R and R prime. What are the operations that I can do on subsets? If I have two subsets of a set, what can I do? Well, composition is something that I can do if I have, composition is going to be the most important of what we discuss. So in some cases we can compose them, and that's a very good idea. But I was looking for slightly more low-hanging fruit, like I can intersect them. I can consider R intersect R prime, or I could consider their union, R union R prime. Or I could look at their set difference, like R set minus R prime, or vice versa, R prime set minus R, right? These are all pretty natural operations that we know how to do on sets if I have two subsets of a given set, right? So for instance, in this example, what is the relation given by R1 union R2? Yeah, so for these operations, I need two subsets of the same set. Here, R prime was just a name, but here for these examples, I'm using these things up here. So let's say all of these are subsets of R cross R, right? These are all subsets of the real numbers, or these are all subsets of the reals cross the reals because they're all relations on the reals. And now I can ask for this collection of relations what unions and intersections are. So what's the union of R1 and R2? What relation is this on R cross R? Yeah, this is the relation of all of the pairs of reals. R1 union R2 is equal to R cross R, or perhaps better it would be written, this is the set of all tuples A comma B such that A is greater than or equal to B or A is less than B. But this turns out to be everything, right? Similarly, I can ask for their intersection. What's R1 intersect R2? Well, in any case, I need, like, the only elements in here are tuples. So this is the empty set. Exactly. This is the set of all tuples A comma B such that A is greater than or equal to B and A is less than B. Are there any real numbers, any tuples of real numbers, such that one is greater than or equal to the other and also less than it? No. There are no such pairs of numbers, so R1 intersect R2 is equal to the empty set, which is, again, a relation because it's a subset of R cross R, right? Like, relations are fundamentally subsets, so we can do subset-like things with them. How are people feeling about this? Feeling reasonable? Cool. I'm happy to hear that. Now let's go on to the nice suggestion of composition. I claim that if I have, so let me say the following. We do indeed want to compose relations. I claim the following. So composing relations. If R1 is a subset of A cross B, and R2 is a subset of B cross C, then I can form the composition R2 composed with R1. And can someone tell me the definition, or what is the correct definition of the composition of these relations? How did we compose functions? So it definitely needs to be a subset of A cross C. So it's tuples A comma C in A cross C, such that what? Right, what we really want is we want there to exist a B in B, such that A comma B is in R1 and B comma C is in R2. Right? In pictures, this looks something like this. We have sets A, B, and C. And I'm going to make a relation between A and B, which is going to look like this, I guess. That's a relation on from A to B, right? And then I'm going to make another relation from B to C, which is going to send this to here. Send all these over here and maybe send this one up here, right? Maybe I should give these names. A, B, C, D, 1, 2, 3, do, re, mi, fa, right? So now we can see precisely which elements are inside the composition of these relations. And they should be all the ways that you can follow a path first from an element of A to an element of B, and then from an element of B to an element of C, right? This is a natural way of thinking about composing relations. So for instance, R2 and R1, here's an element which is in here, A comma fa. Actually, A comma all of these work because, wait, where does A go? Oh yeah, A is going to 1, and then 1's going to all of these things. So A fa, A mi, A re, A do. All of these are inside the composition of the relation. Maybe I should add in C going to 2. This second relation from B to C, does it do anything with 2? Nope, and that's fine, right? Relations don't need to map every element of B to anything over here, right? Functions do, but relations don't care. Relations can be whatever, you know? So my question is, are there any tuples of the form C, comma, something inside this relation? Nope. It kind of dead ends here, right? C maps to 2, 2 doesn't map anywhere. So there are no tuples of the form C comma fa or C comma mi or whatever. And that kind of falls from the definition. There doesn't exist a B and B such that both A, or namely C and 2 is in the first relation, but 2 comma anything is not in the second relation. So we can't have anything like this appearing in this relation. I think that's very clear graphically, well, at least it would be if I could draw better from the picture that I drew, right? Do we have D, do? Yep, you have D, do, because D goes to 3 and 3 goes to do. So since D comma 3 is inside R1 and 3 comma do is inside R2, we must have D comma do inside R2 composed with R1. Oh, you can't see. You also have A comma do. So is this okay? Is this clear? Yes? Or no? This is okay? Okay. This example confused. Okay. What's confusing about this example? Is there anything I can clarify? Oh, right. Yeah, that's true. Yeah, sorry about that. If I drew little circles around them, maybe that'd be better. There we go. Much better. Okay, so this kind of brings us back to our earlier point. Sure you can. My handwriting's atrocious. So this brings us back to our earlier point. If we have R1 and R2 both as relations on A cross B, can we compose R1 and R2? No, right. There's no way to compose these two, just as there's no way to compose two functions from the same set to the same set. What we can compose is when we have three sets that it goes A to B and B to C. Then we can compose. Now, a special case of that is if we have R1 subset A cross A and R2 subset A cross A. Can these relations be composed? Now these relations can be composed in either direction. I can either do R1 composed with R2 or R2 composed with R1, right? Because any way you set it up, you're always going to have A, and A when you want to draw your little picture, right? Whatever, in either direction. So that's why I wanted to be a little careful about when you can compose relations. Does that make sense? Okay, so let's play around with some compositions of relations here for a little. So if here's a generalization or a definition. Let R be a relation on A. Remember, this means that R is a subset of A cross A. Then we define R to the n. This is like the nth composition of the relation R recursively. So R to the 1 is just equal to R, and R to the n plus 1 is equal to R to the n composed with R. So I think that this definition is reasonable and understandable, but the first thing let's examine is the following. So example, let R be the relation on the set of people such that A comma B is in R if A is a parent of B. Okay, so my first question is, what is the relation R squared? Well, by definition, R squared is R composed with R. And when is an element inside this composition? Well, here's how I find an element in the composition. An element A comma C is in R composed with R if A comma B is in R and B comma C is in R, right? We just defined what composition of relations are. If A is A, what if B? I'm a little unclear. I still don't understand your question. example, the set of people such that A comma B is in R if A is a parent of B. So by definition, R squared is equal to R composed with R. How do I find an element in here? Well, I need to find an A comma B in here and a B comma C in here. And if I can find such a pair, such that I have A, B, and then B, C, then A comma C is in R composed with R. What is the relationship between A and C if I can find an A, B in R and a B, C in R? No, it wouldn't be just the same as R, because what I'm saying here very concretely in terms of people is A is a parent of B and B is a parent of C. Exactly. So R squared is the grandparent relation. A comma C is inside R squared if, first of all, A comma B is in R. So A is a parent of B. And B comma C is in R. So B is a parent of C. So A is a grandparent of C. Yes, that's precisely correct. R cubed, which we'll get to in just an instant, actually. So in other words, is it somewhat clear to you now that if R is the relation A is a parent of B, then R squared is the relation A is a grandparent of B? Because how did we find elements in R squared? We found a pair of tuples such that there was a common one in the middle, right? We need A to be a parent of B, and we need B to be a parent of C. Then we compose them, and A and C are related in R squared. Is this okay? Great. Anyone have a moment of confusion? Anyone have a further question? Okay, let's examine the next one. So here I'll say R squared is the grandparent relation. So now let's examine R cubed, which by definition is equal to R squared composed with R. What does it mean to find an element inside a composition? To find an element inside a composition, so if I want A comma C, let's do different letters. A comma D inside R cubed, what do I need? Yes, I need A comma B inside R, A comma B, and I need B comma D inside R squared. Notice that when I write a composition, things kind of look like they're in reverse order. This is the same thing with functions, right? This is telling me first I go from A to B, and then I go from B to D. So don't be thrown off by the order in which I write compositions. So I need A, B, in R and then BD in R squared. So this means A is a parent of B and B is a grandparent of D. A is a parent of B and B is a grandparent of D. So what is the relationship between A and D? Yeah, this means AD is inside R cubed if and only if A is a great grandparent of D. Yeah, so one last time, when I write out compositions, I write them out in this way, but really this means that I found in the set of all people, I found a person A, and then here's people, and here I found a person B, and then lastly over here in people, I found a person D. So even though like the thought is A, B, and then B, D, and this is correct. I want to kind of concatenate these into A comma D, but when I write it as a composition, I write it this way. So first I go from A to B using relation R, and then I go from B to D using the relation R squared. Is that okay? So we see that R to the N is the nth ancestor relation, right? You can do this as often as you want. Okay, let's do a fun proof now, which I enjoy. Theorem. A relation R on a set A is transitive if and only if R to the N is a subset of R for all N is equal to 1, 2, and so on. So this is a way of describing a transitive relation in terms of properties of its composition. Okay, so proof. Someone tell me what I need to prove in order to prove this statement. If I'm trying to prove an if and only if, what does that mean? Right, I need to prove both ways. I need to prove A is transitive implies R to the N is a subset of R all the time. And in the other direction, I need to prove if R to the N is a subset of R, then I get transitive. So let me first prove this direction. So I'm first going to show, first I show that if R to the N is a subset of R for all positive integers, then R is transitive. Right? I claim that I actually, for this statement, I don't need the full weight of this subset. I actually only need to use that R squared is a subset of R. So we assume that R squared is a subset of R. Right? This is a weaker statement than R to the N is a subset of R for all N, right? This is just one of these positive integers. And we wish to show that R is transitive. So let A comma B in R and B comma C in R, right? The definition that I want to kind of check is I want to check if I have such a chain in R, namely A comma B and B comma C, I want to show that A comma C is in R. Do we agree that that would mean that R is transitive? Right. But what do I know about A comma B and B comma C? If I have A comma B in R and B comma C in R, what can I do naturally? Well, I don't think I can immediately say that A comma C is in R, but I can immediately say that A comma C is in R squared. By definition of composition of relations, A comma B in R and B comma C in R implies A comma C is inside R squared. But R squared is a subset of R, so A comma C is in R. Thus, the relation is transitive. Any questions about this part of the proof? So maybe the way to kind of think about these things now is if you see an A comma B in R and a B comma C in R, you immediately know that A comma C is in R squared. That doesn't necessarily mean that it's in R. If it is in R for all such tuples, then R is transitive, but not every relation is transitive. But every time that I have A comma B and a B comma C, oh, I know A comma C is in R squared. Yeah, here it's enough, like here, all we need to examine is R squared, right? Here, I'm assuming Rn is a subset of R for all n. That's a really strong assumption. It turns out that I only needed, for this direction, I only needed R squared. Right? Because here I'm just trying to show that if R to the n is a subset of R, then I get transitivity. Well, I can use a weaker assumption to prove transitivity, so I'm fine here. Is that okay? Are you comfortable with why I don't need to do stuff with higher integers in this direction? Okay, so the point kind of, I mean, this goes back all the way to essentially I have extra things in my premises that I'm assuming here. Here I'm assuming R is a subset of R. I'm assuming R squared is a subset of R. I'm assuming R cubed is a subset of R, and all the way up, right? Those are my assumptions. So I've got this and all of these. And in the first part of this proof, I'm trying to show that assuming all of these is enough to show that R is transitive. Do you agree that this is what I'm trying to show? I've got all these assumptions. I'm trying to show that, right? But it turns out, I mean, just going back to logic, sometimes you don't need all of your propositions to show something. Sometimes you only need one or two, and we only needed this one. But now we're going to use all of them when we go in the other direction. So now assume, so I'm going to do this direction. We show R transitive implies Rn is a subset of R for all positive integers, n in z greater than 0. If I'm trying to show something about all of the positive integers, what proof technique should I use? Yep, I want to use induction here. We prove this by induction. What's our base case? Our base case is R1. I want to show R1 is a subset of R, but remember R is equal to R1. Since a set is always equal to its, or since a set is always a subset of itself, the base case is proven. Okay, now for the inductive step. What should our inductive hypothesis be? Yeah, we assume that R to the K is a subset of R, right? And now what we want to show is that R to the K plus 1 is a subset of R. We wish to show R to the K plus 1 is a subset of R. By definition, what is R to the K? Or R to the K plus 1? Right, it's R to the K composed with R. So an element in R to the K plus 1, so an element AC is inside R to the K plus 1 if there exists A comma B inside R and B comma C inside R to the K. Right? And we want to show that A comma C is inside R, because I want to show that R to the K plus 1 is a subset of R. So I produced an arbitrary element of R to the K plus 1. It's AC is inside here if A and B is in R and BC is in R. Right? In parentheses, I want to say we want to show A comma C is inside R. Okay, where should we use our inductive hypothesis? What is our inductive hypothesis? Our inductive hypothesis is that R to the K is a subset of R. So the element BC, which is a subset of, or which is an element in R to the K, by our inductive hypothesis, yeah, B comma C in RK implies B comma C is actually in R. So for an arbitrary element of R to the K plus 1, which is formed by taking an A comma B in R and a B comma C in R to the K, my inductive hypothesis says that B comma C actually lives in R. And now what do I need to use? A comma B is in R, B comma C is in R. Why can I say that A comma C is in R? No. We are assuming something about the relation R. Yes, R is transitive. Our inductive hypothesis led us to be able to say that this B comma C in RK was actually an R. Now, by the transitivity of R, since A comma B is in R and B comma C is in R, A comma C is in R. So R to the K plus 1 is a subset of R. This completes the induction. This is a cool proof. This is fun to me, and I hope it's fun to you, the way that we're using all of these things together. This proof has a bit of everything. It has some set theory, it has relations, it has induction. It's got a lot of stuff that we've discussed in this class all coming together. So I like it. That's about all for today. Any questions? Cool. Yeah, absolutely. Yeah, everyone have a beautiful weekend. That is the point. Everyone have a nice weekend. Relax. Don't feel cortisol pumping through your brains. Hey Shreya, do you have any questions? I'm gonna stop the recording, but